So we said that we have certain design requirements, and then we put them at flexural or bending requirements, like strength requirements, if you like. This is going to be like the typical that we usually see in any concrete design, whether it's going to be pre-stressed or non-pre-stressed, like conventional concrete design, exactly the same checks. So the requirements, like for example, flexure or bending, you want to be sure that you have enough strength that the demand. Also, you'd like to check the shear and torsion. If there is some torsion on the beam, you need to be sure that you have enough ties and the stress is going to be within the allowed or within the code limits. Also, you need to do serviceability checks for deflection and for cracking, and in some cases for vibrations. Vibration is not really mandated by any code, but it is one of the good requirements if you are expecting lots of traffic, or let's say if you put some pre-stress in a mall or parking structure, since you're going to have traffic here, you want to be sure that vibration is not going to be an issue. Otherwise, everybody's going to be scared of excessive vibration. People is not going to be able to take it, you know. In pre-stress, as we said that we're going to have here stages for the design and checks. We said at the time when you transfer the pre-stress force to the concrete, remember? And then you're going to have some limited state at service load and then also at failure. So previously, we were just talking about the pre-stress force transfer and the limited state, but we never talked about the design strength. Now today, we're going to be covering design strength and the limited state at failure. This is also a repeated slide. So this is also, as you remember, that this is also a repeated slide. Nothing is new here. We're going to be doing here the limited state at failure. Also a repeated slide that shows the stages of loading. At the beginning, you're going to be doing here the pre-stressing, and then you start to load it with dead load or self-weight. And then after that, you're going to be adding the additional dead load. So this can be like the progressive stresses, if you like, progressive stress distribution, if you like to call it this way. At the end, you need to find out the strength of the beam. This stress distribution is going to be very similar to that of the conventional concrete design. And to make it easier, if you guys recall in concrete design, we made this compression block. So we said witness block, we're going to be using a block. It's going to be like this. It's going to be 0.85 F prime C, and the depth of it is going to be called A, and so forth. So this is going to be the stage of stress that now we need to check it for. On this load deformation, like deflection analysis or curve, we said that we're going to have some camber. So this section here includes a camber, which is going to be kind of negative deflection because the beam is going to be going upward. And this is when the beam is going to be deflecting downwards. So all of this curve is going to be deflection downwards. And then at a certain point, we're going to say here's going to be the capacity point, which is the ultimate. And again, this is going to be the stress distribution that instead we're going to replace it with the compression block, witness compression block. Now you're going to have a demand, and in the same time also you need to figure out the capacity for this demand. Your demand is given in terms of moment. This is like this slide here includes all the load combinations according to the code for the current design. Most likely in this course we're going to have only dead load and live load. So I'm going to have here D and L. Sometimes we have roof live load, but usually we're just going to call it here dead load and live load. Most of this load combinations wouldn't apply because I'm not going to be adding here wind force or earthquake forces or snow or earth pressure. Most likely it's going to be only dead load and live load. Therefore, the only two load combinations that I need is going to be these two load combinations. I'm not going to have T or F. What is T and F? You can look it up here. This if you have a tank, and T if you are going to have temperature change, major temperature change. So these two load combinations, you should be able to figure out the ultimate force. We call the ultimate force. We also call the factor force. If you're talking about moment, is going to be M sub U, shear is going to be V sub U, and P is going to be P sub U. So this is going to be the demand that you're talking about. It's going to be axial moment, shear, and torque. Just in case if you have torque, it's going to be also T sub U. For this slide set, we're going to be working on M sub U. Moment demand, factor demand. It's going to be moment. So in this case, you're going to be doing here 1.2 M dead load plus 1.6 M live load. You compare it with 1.4 M dead load. In this case, dead load is going to include self-weight and superimposed dead load. It's going to be the total dead load. It's going to take this factor here, 1.4 at one load combination. The other load combination is going to be 1.2 times dead load. Now again includes self-weight and superimposed dead load. Now you need to compare it with Feynman, which is a strength. We call this going to be the strength. The design moment is going to be this M sub U. So different names or terms for this. I'm going to say here design moment, factored moment. What else? I need your help.
Ultimate moment.
Ultimate moment, yeah. Anything else? Any other names? I guess this should be enough, right? How about Feynman? What would you call Feynman? You have names for it? I'm gonna start here by saying moment capacity. Anything else?
Nominal moment.
What?
Nominal.
Nominal is gonna be only Mn. Once multiplied by phi, it becomes the moment capacity.
Oh, got it.
Yeah, it's very close. What else?
Allowable moment?
No, it is not allowable. Because if you do allowable, it means that you are doing an ASD design, allowable reference design. Right? I'm gonna call it here moment strength. Because this method here is called strength design. Any other names that you may think about, that you heard about, and maybe you'd like to see if this is gonna be about the design or it's gonna be about the strengths? So I'm gonna call it here moment capacity, moment strength. What else? Also, you can say flexural strength. What's wrong? It doesn't like it, but this is fine. This one also, I can call it flexure demand if you want to. Also, I can call this moment demand, right? I guess it's gonna be about all the names that I hear about, most likely to be used in practice and engineering document. This is gonna be about it, right? You wanna be sure that you have enough capacity more than the demand. And usually you don't have the capacity to start with. To start with, you're gonna have the demand, and then you need to pick a section for the member, whether it's gonna be like double T or it's gonna be a beam. And then after you pick the section, you're gonna pick up the number of strands that you put in there, and then you figure out the Feynman, and then you compare it with M sub U. This is usually the steps, the standard steps. I'm gonna take you back here to a very old slide that also we have seen earlier in this course, which is about conventional concrete design. Let's assume for a second that we have rectangular section. It is not a T section, and we don't have any compression reinforcement. Just to make it simple, we assume that the steel is yielding. So this is gonna be our first assumption. We assume that the steel is going beyond the yield point for the material itself, and therefore the stress in the steel is gonna be equal to F sub Y. So now the steel is yielding. Take the yield strength of the steel, which is typically 60 KSI for A-steam A615, multiplied by the cross-section area of the steel, AS, is going to give you here the total tension force on the steel. So you just take this cross-section area of all the steel, multiplied by F sub Y, you get here the tension force. We consider here the distance from the top compression fibers. So here's going to be compression. in this section. Say compression is assumed to be within this range. All the way to the centroid of the tension rebars. This is going to be critical. Where do you take it to? Let's say that you have 2 lines of rebars. You take it to the centroid of this rebar group. So let's say that I have here 1 line of rebars, just going to make it simple, and another line of rebars, right? Instead of showing all of this circles for the rebars, I'm just going to make it this way. So you look for the centroid, and these can be the distance from the top compression to the centroid of the rebars. Now, you need to figure out this A, the compression block depth. So the way that you do it, you set this compression is going to be equal to the tension force. Compression force, we assume that we have uniform pressure in this block over this area with a depth of A. So you say 0.85 F prime C for simplification, multiplied by A, multiplied by the width B. With that, you get the compression force, like in this equation. Now you said C is going to be equal to T. Again, you start with having number of steel rebars that you provide there, which means this tension force is known. In this compression force equation, you have everything except for A. So A is going to be your unknown. I'm going to say this is going to be your unknown here. You said C is going to be equal to T, you solve for A. Once you solve for A, you say, here's the moment arm from tension to compression. It's going to be equal to the depth minus A over 2. You take this tension force, and then you start to take the moment about this point. So what do we do here? Take the moment about the compression force. Let's say here, take the moment about this point. Sum of the moment about this point. Someone's going to say this is like a couple. If you just take tension compression and the distance between them, you say C or T equal multiply by this distance. You can do it this way if you want to. But also you can say, I'm going to be taking the moment about this C point. Therefore, the moment, internal moment, because this is here 2 internal forces, it's going to be equal to the tension force multiplied by D minus A over 2. You say this distance is going to be D minus A over 2. I want to do it this way because for me it's going to be simpler, and I'll need this for pre-stress. When we come to pre-stress, it's going to be very helpful. So good. I mean, it looks simple for conventional concrete. At certain point also, I need to confirm that the steel is really yielding, and I need to figure out the phi factor. So usually we consider the concrete to be failing at 0.03, and from these 2 similar triangles, I should be able to figure out the strain in the steel. Once it goes beyond the yield strain, and how much is yield strain? Can someone help me with this? How much is this? For grade 60, so I'm going to say here grade 60 steel. The strain in the steel is how much at yield point?
Is it 0.002?
Yeah, where this is come from?
For my other courses, the yield strain.
Okay, so I'm gonna say here the strain. I'm gonna say ES, E lowercase is gonna be the strain. Okay, it's gonna be equal to 60, grade 60 KSI divided by 29,000. Can someone try this, please? Yes, I need help. Just 002 or 00207 or what?
0.006.
Okay.
0.06.
Okay. So I want to be sure that the strain in the steel here is higher than this value. Otherwise, my assumption is wrong. And I need to repeat my analysis. And this going to be one of the unknowns. And instead of just having one unknown to be the A, now I'm going to have A and the strain in the steel. It's going to be 2 unknowns, 2 equations, solve them together, and then get the answer. But usually, I hope that I have enough strain in the steel just to make it easier for me. Here's the equation. Here's the tension force. Assuming that the steel is yielding, compression force, set them equal to each other, solve for A, find out Mn, and then multiply by the phi factor. How to find out the phi factor? If I may jump here, guess say I have this chart by the code, and I have it also in this slide set. I have more than one slide set for you. So once you solve for the strain in the steel, let's say the strain in the steel turned to be right here, 0.002, which means at the yield point. Now you're going to be using this other. You don't have a spiral case. This is not a column. It's going to be a beam. So your phi factor is going to be 0.65. But if you solve for the strain in the steel turned to be in the tension control failure or performance, your phi factor is going to be 0.9. And this is what we'd like to see our beams at. Any questions on this chart? You guys, you have taken it previously in 408 and maybe other courses, right? And you have it available in the ACI 14, 314, 318, 14. So now I understand this. This is going to be for non-pre-stress. This is going to be the flexure strength or design strength if you want to. Also, we have this type of beam analysis that we do when we have compression steel. If you recall, we have here compression steel, we call it S prime at the distance of D prime. We assume that the bottom steel is yielding and also the top steel is yielding. And then we assume two couples. And simply because I'm gonna have here two compression forces. The first compression force is gonna be on the concrete. The second compression force is gonna be on the steel itself. So I'm gonna be taking this one tension force split into two components just to have two moments or two couples, if you like. And then at the end, I'm gonna say this force is gonna be equal to that force, and this T2 is gonna be equal to C2. Two couples, I'm gonna have C1 times Z1 plus C2 times Z2. So this is also the way that we treat the beam this way. Beta factor is gonna be this critical term to find out the C, the neutral axis depth, because it relates C to A, compression block depth, witness block depth, to the neutral axis depth. Ratio is beta 1, and beta 1 depends on the concrete strength. If the concrete strength is going to be 4,000 or less, your beta 1 is going to be 0.85. Once you hit 8,000 or more, it's going to be 0.65. In the middle, you can do this interpolation with this equation. So this is going to be the equation for interpolation for beta factor. For each additional 1,000 psi or 1 psi, you're going to have a drop of 0.05. Meaning, for 4 psi concrete, how much is beta 1? We're going to say beta 1 equals 0.85. When it becomes 5 psi, beta 1, I'm going to drop it here by 0.05, right? I'm going to say it's going to be equal to 0.8. Just drop it by 0.05, according to this equation. How about with 6 psi? Beta 1 equals to what? 0.75. It's going to be that simple. This phi factor, we went through it. We know about this from the 408 course. This is going to be simple. You figure out the strain in the steel, and once you have it, you can find out the phi factor. Another way of doing it is to find out C over D. What's C over D? I'm going to take you back here. You find out the ratio of this C over D. This C over D, once you have C over D, you can find out the phi factor. But be careful, because direction increase of C over D, it goes this way. And look at this. It shows here 0.6, and here's going to be 0.375. Direction of the strain in the steel, direction of increase in the chart is going to be coming this way. So just be careful about this. If I give you here C over D, I'm going to say equals to 0.5. Where would you go? 0.5 means you're going to be in the transition zone, right? If you're not careful about direction of increase for C over D, you would have gone to this tension control. You say 0.375, here's 0.5, right? But this is wrong. It should be in the middle here. So be careful about direction of increase. Now we need to talk about pre-stress beams. So the previous slides was just about conventional concrete. I'm going to have here tension steel, and sometimes I have compression steel. Now here's the new thing. I'm going to have here pre-stress strength. So if you look here, this is going to be the actual distribution for the stress in the concrete. And this little piece is going to be for the tension. Usually we ignore this. We just ignore it totally. And the total cross-section area is going to be called APS for the pre-stress strength. In the past, we used to say F sub Y. This is going to be the stress to be used in the steel. We assume that the steel is yielding, and then we use F sub Y. In our case here, we're going to be using FPS. I understand from the previous lectures that we have something called FPU, which is the ultimate. We have also FPE, we have FPI. Do you guys recall the symbols? What is FPI? I need your help in this. What is FPI? What definition of FPI? Anyone recalls?
The initial pre-stress.
Initial pre-stress. And what value do we usually use for FPI? I'm going to list them here. FPU is how much? Anyone recalls FPU for 4615?
It's a 270.
270 KSI. Good. FPI is how much? Typical value. You guys recall this value? At the time of
Yes.
pre-stress? And FPE is how much? 150, right? KSI, correct? You guys recall these three values?
Yes.
Okay, now I'd like to add also FPS. So where do you think FPS is going to be? Can it be more than 270? 270 at failure. Can I design for failure?
No.
No, it's going to be too much. Is it going to be above 189 or below 189? Is it above 150 or below 150? I need to have a feeling for it, right? For the ultimate point. So I'm going to say, let's go back to this slide here. I'm going to take you back to this slide just to have an idea what value do you think we're going to be at. FPI and FPE is going to be in this range here, right? It's going to be about here. Here's the service load, and this is going to be the initial. We're going to be here, right? So it seems that this is going to be the ultimate is going to be higher than FPI, but also is going to be lower than FPU. Meaning I'm expecting a value to be right here. I'm going to say FPS equals. Remember this. FPS equals. I'm going to leave it here because we need to discuss it, right? How much is this FPS? It's going to be some value. It's going to be lower than 270, but it's going to be higher than 189. So I was going to say, but when you stress the strands, you're going to stress it only to 189, right? How come you can consider stress higher than the pre-stress that you initially put to the strands? You say, well, let's go back to the same slide. We're going to go back to it. I want to understand what's happening here in this curve, because we discussed this area here, but we never discussed what's going to happen here. Now, when you put loads on the beam and you are approaching here the capacity point, the beam is going to be deflecting and you're going to be adding tension to the strands. This tension to the strands, you're going to be adding it, and you need to be careful because you don't want to go beyond 270 KSI. If you have this curve, let's say that you have the steel curve for the strands. I understand that you're going to applying here load, right? Now you're going to be adding more stresses to the strands, but you never be able to approach FPU, which is this value here. So you need to be right below this. But I don't know exactly what value because we need to work on it. We need to study it. But this is going to be the value FPS that you need to use in your analysis. This stress distribution is kind of hard to work with. So it seems to me now I should be able to use witness block. Here's the block, compression block. And the compression force is going to be equal to 0.85 F prime C times B, the width, times A. It's going to be the integration of the stress over this area. And the tension in the strains is going to be equal to APS times FS. Now, I guess you should be able to solve for A, because in this equation here, FPS, you can come up with some value. Later on, we're going to determine a value. Code is going to say, here's the value for APS. And APS, you can estimate number of strands, like what we have done in previous homework. Set T is going to be equal to C. Now you solve for A. It's going to be your unknown that you need to solve for. Once you solve for A, it's going to be very standard, very similar to conventional concrete design. You need to find out D minus A over 2, multiplied by C or T, and then you have also the phi factor that you need to work on. Now it becomes like any other concrete beam. Now, the new symbols that you're going to be seeing here, this is going to be the difference between concrete design, conventional concrete design, and pre-stressed. It's going to be APS instead of AS. It's going to be FPS instead of FY. And also it's going to be DP. What is DP? DP is going to be the distance from the top compression fibers, right, all the way to the centroid of the tension steel, or to the strands. We're going to call it here DP. If you see here this symbol, it's going to be DP. Okay, let's look here. This is going to be called here APS. It's going to be called here DP. And the equation, the rest of the equation is going to be very similar to that of the conventional concrete design. Now, someone's going to say, would that be okay if I'm going to be adding some pre-stressed strands in the same time with some AS, some conventional steel? For example, you can add here, here's going to be the pre-stressed strands, and right below it, I can add maybe 3 rebars if you want to. And what's your reason for this rebars? You're going to add also some rebars top and bottom, and then you say, I'd like to control the cracking of the beam, and I want to be sure if someone's going to put this beam upside down, it's not going to be failing. Like what you have here in your homework 5, right? If you recall it, the beam failed because of excessive tension. It couldn't take it once you put upside down. So once you add here some conventional rebars, like number 4 or number 5, you add few bars top and bottom, is going to help in the strength, and also is going to be help to control the cracking in your beam, and also for fabrication and hauling the beam from one place to another place. So in this case here, I'm going to have here AS and APS. I'm going to have here DP and just D. And my moment is going to be based on the combination, the effect of APS and AS. And we're going to see this in a minute from now. Any questions?
So the FPS is like for service, right? Like the S?
It is not for service. It's going to be for the ultimate point. It's going to be for the capacity point. If I may go back here. For example, when I go here to any beam design, let me go here to this beam design. What is FY? Is this for the service? Or this is at the capacity point?
The capacity.
The capacity point. So very similar to what we are doing here in conventional concrete, I need to come up with similar value to this. So instead of AS,
Okay.
I'm going to have ASP, and instead of FY, it's going to be PS or SP. Sometimes called PS, sometimes SP. So very similar to what you have in conventional concrete. We have APS and FPS. But when it comes to discussion of FPS, we need to discuss it. We're going to be talking about this value. Where do you bring it from? So in this case, as I said, you may have conventional rebars like ASTM 615 and also 416, which means some strands at the same time you have also some rebars. Total tension force is going to be based on this combined effect: conventional rebars and pre-stressed strands. So it's fine. How about the compression? I'm going to say compression is going to be the standard 0.85 A prime C B times A. Let me go back one slide. It's going to be this force here. So in this case, I'm going to say T is going to be equal to C. Here's the total tension force again. These two terms. Now I guess I should be able to solve for A. If I can have good estimate for the amount of reinforcing bars, the amount of pre-strands, the cross-section area of the pre-stress strands, and FPS, I can solve for A. Now, how do you find out the moment? In this case, the moment, I'm going to be taking the moment about the compression force. So I'm going to take you back here to this slide. I'm going to be looking at this section. I'm going to say in this case, I'm going to have here one tension force for the pre-stress strands. Another tension force is going to be for this conventional rebars. Let's say it's going to be right here. The distance from here to there is going to be called D, correct? It's going to be called D. Now let me take the moment about this point. So we're going to be taking the moment about this point. This one here, I'm going to call it, if you don't mind, I'm going to be calling this tension, just to differentiate between this tension force and the other force. I'm going to call this, is going to be T. I'd like to use TPS. It's going to be equals to APS times FPS. And the regular tension force, which is this force here, I'm going to call it T, is going to be equal to AS times Fy. Now let's start here by taking the moment about this point. How many forces do I have when I take it about this one? I'm going to say I have here two tension forces. I'm going to have here TPS multiplied by dP minus A over 2 plus the conventional force, conventional steel tension force is going to be equal to T times D minus A over 2. So I combine here the two forces in one equation. And this is going to be M sub N. At the end, you need to multiply by phi factor. And this is exactly what you have here in this equation. It's going to be the conventional rebar effect, or factor, or moment, or term. And this is going to be the pre-stress strains effect. This one here includes APS, FPS, DP, and this is going to be AS, FY, and just D. At the end, you multiply by phi factor for the whole thing.
I have a question, Professor. Could you
Yes.
please briefly explain what is the difference between APS and AS?
Absolutely. Yeah, give me a second.
Sure.
You remember this concrete design, right? Conventional concrete design. This slide set number 2. And then you put some reinforcing bars. We have an example. And then we put 3 number 8. That was conventional concrete design. You remember this or no?
Yes.
Okay, then. Very good. What did we call this? I mean, for the cross-section area of the steel. Do you remember? We call this AS.
Right.
AS is going to be the amount of cross-section area of the tension steel, and this is what we call here conventional steel, conventional rebars. Like what? Like number 8, number 7, number 6, and I guess we have a table for this, right? We have a table that shows all the size, and where do you take it from? I'm not sure if the table is here. Okay, it's right here. You remember this table, right? And you are aware of it.
Yes.
Okay, very good. So this one here we call it AS, and it's going to be the conventional cross-section area for the reinforcing bars. We did this slide set last time, which is number 6. And we talked about also in slide set number 5, we talked about in the material section, and we talked about this grade, the 416 strands. You remember the strands?
Yes.
Good. In the strands, we said that the strand is going to be 7-wire strand, is going to look like this. And then we said that we're going to be using this table for the strands, right?
Right, right.
We said it's going to be 270. And for half-inch strand, the cross-section area is going to be 0.153, which is going to be completely different table and different information, different grade from the conventional rebars. We call this a strand.
Oh, so we basically use like a bunch of cables instead of just a single rebar. That's the difference, right?
Yeah. So
I
in this slide here, what I used APS for the pre-stress strand cross-section area.
Right.
And this one here, I used AS, if I may call it here AS, for conventional rebars.
Right.
In this case, I may have combination of pre-stress strands and conventional rebars in the same section.
Oh, okay. Okay, now it makes sense.
All right.
Thank you.
No problem. So what you have here, this is going to be the conventional rebars, like number 5, number 6s. And this is going to be the pre-stress strands, like half-inch 416, which is going to be taken from this table, right? Look, this is going to be taken from this table. It's going to be cables, like the one that you have used in your last 2 homeworks.
Yes.
Okay. So I'm combining here the conventional rebars with the pre-stress strands in one design equation.
Right.
In some equations, or in some cases, you're going to have only pre-stress strands, and in this case, you're going to be eliminating this conventional strand, the conventional rebars. In some cases, you may have conventional rebars with the strands. In other cases, you may have just conventional rebars, and this is going to be taking you to a design equation like in this one, right?
Right.
This
Right.
one here, I just have the conventional rebars, like number 6s and number 5. So I can play with this. At one time, I can have both of them, or I can just eliminate any one of them and solve exactly with the same equation. So this kind of like more general equation for the flexure strength. And at one time, you can take this out or keep it, take this out or keep it. It depends on what reinforcement that you're planning to put in your
Right.
beam.
So we use it basically to prevent cracking.
Which
Right?
one?
Is for
The
APS?
conventional? The conventional?
Yes.
Now, this pre-stress strand is going to be much stronger than this, right?
Absolutely.
All the grade is going to be 270.
Yes.
For the conventional rebars, the grade is going to be 60.
Oh,
So
I
I'm
see.
going to say, why would you add this if this is going to be enough? I mean, you have lots of these, right? For each
Yes.
one of this one, it is equivalent maybe to 3 or more than 3 of this rebar.
Right.
So why would you use this? So the answer is, this is cheaper. It doesn't need any pre-stress. And also it helps you in control the cracks. When you do top and bottom, you can control the cracks.
Right.
And just in case, if you lose the pre-stress, if something wrong is going to happen in your beam, so at least you have some strength to support the beam.
Oh, that's
More than
interesting,
one
actually.
reason. You don't want to put all the eggs in one basket, if you like to think about it this way.
Right, right, right.
Because if the strand is cut or damaged, you're going to have some residual strength left over. You can use.
True. True. Thank you, Professor.
No problem then. Now I'd like to look here at this FPS. We said, what is the value of FPS? How can I find it out? The code here gives me an equation for FPS that's going to be used in calculation of the strength of the beam. So this FPS is going to be equal to FPU. How much is FPU? Anyone recall the value? For the 416?
270.
416? 416. I'm going to say equals 270 KSI. Very good. And this factor here, it says 1 subtracting minus. So I guess this number here cannot be more than 1. Am I correct? Because the whole thing here, it needs to be less than 1. It's going to be fraction of FPU. And I indicated that this is going to be most likely more than 189 KSI. So I need to go through this equation and look at all of these values. It says here beta 1. I'm going to be going here to certain items that you guys are aware of, so that we say now this is covered. This one I need to work on it, right? I need to have more values. So maybe looking at this, I'm gonna say beta 1. Did you guys hear about beta 1?
Yes.
Yeah, this is gonna be
Yes.
the ratio between A to C, right? I said, okay. How about this FPU? Do you have FPU? So
Yeah,
yeah,
right.
give me like this value. I have it. I know this. And F prime C, do you have it? You hear about it? Yeah, we know this value here. How about D and DP? We have D and DP, right? You see, good. I also have this covered. How about F sub Y is gonna be for the conventional steel, the regular rebars, and between F prime C? Yeah, I have this, right? I have all of that. How about this rho? I'm gonna say rho is gonna be the steel ratio. Look at this at the bottom. It's gonna be AS divided by BD of the beam. So I'm gonna say, yeah, I have this rho. I know definition rho. I can figure this out. How about rho prime? I'm gonna say for the compression steel. If you have any compression steel, right? So I have all of this section now is covered. I know all of that. How about this rho P? What is rho P and what is gamma P? This is gonna be now the two new items. Rho P is gonna be the pre-stress steel ratio divided by BD, very similar to this. You see this rho? It's gonna be for the steel, conventional steel. Rho P when you take APS divided by BD. So now I know this. So only one item that I need to learn about, which is this gamma P. And it says go to this table. So I'm gonna be going here to this table to see what value to be used. In the code, we went through this already, and then we say this is gonna be FPY divided by FPU is gonna be, let's say, 85%. I have another table that says when FPY divided by FPU is gonna be more than or equal to 0.85, gamma sub P is gonna be equal to 0.4. So I'm gonna say here, let's take it as 0.4, according to this information from the code. It's gonna be that simple. Now I need to go back here to this equation. I'm gonna say this is gonna be 0.4 and this could be 0.8, 0.75, depends on the strength, and this is gonna be based on the properties of the beam. So okay, good. It seems now I should be able to solve for this FPS as a fraction of FPU. I have a condition here in the code that says if D prime is gonna be more than 15% of DP, compression reinforcement should be neglected or shall be neglected. So I'm gonna say what is D prime? You guys remember D prime? Anyone remembers D prime?
Yeah, the compression steel, the distance.
Yeah. I'm gonna say this is gonna be 18. Okay, let me go back here quick. Just in case, if you're looking for D prime, it's gonna be the depth location of the compression steel from the top. They say if this D prime is gonna be more than 15% of DP to the pre-stress strength, ignore it. Okay. It's gonna be the first condition. Second condition, it says if compression reinforcement is included in this equation, which means if you have this rho prime, you should not take this to be less than 0.17. This term. What is this term? You see, this term is this term here. See this term? You say if you have any compression, steel, don't go with this. What? As it says here, below 0.17.
Professor?
Yes.
I'm still a little confused on rho P.
Rho P is going to be the ratio of APS divided by the cross-section area of the concrete. The steel ratio. Rho is a steel ratio, okay?
Oh, okay.
Rho, generally speaking, is a steel ratio.
Thank you.
No problem. So generally speaking, again, rho is going to be the steel ratio, right?
Yes.
So when it comes to just rho, is going to be the cross-section area of the reinforcing bars to the cross-section area of the concrete. When it comes to compression, steel ratio, like what you see here, is going to be AS prime divided by BD. Now the question is, what is this rho P? It's going to be APS divided by BD. It's going to be very similar to it, but it's going to be for that pre-strength, the pre-stress strength. This is okay. Now let me see what moment do I need to determine if I'm doing here a design for a pre-stress beam. The first one is going to be the cracking moment. I'd like to evaluate the cracking. I need to know when the cracking is going to happen. Because in certain cases, I'd like to have uncracked beam. And I want to be sure that the beam is not going to be loaded to the cracking point. This is going to be number one. Number two, I'd like to see where I'm going to be at in terms of the cracking versus the demand. For example, do you think the beam is going to be cracking at maybe half the way when I apply the loads? Or maybe the beam is going to crack maybe at 90% of the applied load, which means cracking is not going to be too much. Or do you think that the beam is going to start to crack once I'm going to start to apply any loads to it? So you'd like to see here where the cracking, when do you think the cracking is going to happen in terms of the load progressive? So in order for you to do this, you're going to say the cracking stress, this beam is going to crack at 7.5 square root of F prime C when the tensile stress is going to be exceeding this value. And this is going to be here the generic equation, the general equation that I have for any stress at the bottom, because usually it's going to be simply supported beam, tension is going to be at the bottom. And they have this generic equation, and I'm looking here when the stress becomes at PE, or the force becomes here at PE, the effective, which means all the losses has taken place. So when you look here at this equation, you're going to be saying it is true that the stress or the force is going to be at PE, but the moment is going to be the cracking moment. It is not going to be the total moment in this case, because I'm looking here for the cracking moment. So I can take this equation, rewrite it. When the stress at the bottom becomes equals to FR, the moment is going to be right at the cracking point in this equation. And the force in the strands is going to be at PE. It's not going to be at PI, because you're looking here at the service case. You know, after maybe a couple of weeks, you're going to be losing the force from PE, from PI to PE. So we're already at PE here. So I'm going to be taking this equation and write MCR here and write F sub R right on the stress side. I can rearrange and put MCR on one side. This is going to be my goal, is to find out the cracking moment based on all the other stuff. This is exactly what we have done. I'm going to have here one equation for the cracking moment in terms of PE, eccentricity, section properties, and the stress at the cracking point, which is this value here, 7.5 square root of F prime C. It's going to be that simple. So for phi mn, I have an equation for it. I'm going to go back here. Depends on FPS and APS and the amount of steel that you put there. And for the cracking moment, I can take the stress equation, rewrite it, and find out the cracking moment on one side. And this should be sufficient for my design for a pre-stress beam. Any questions?
How many problems? Oh, sorry.
Oh, sorry about that. Does that equation also include the extra rebars like that you want to add, or just the cables?
In this case or in this case? You're talking about this one here for this equation, correct?
Yeah. Does that include those extra rebars? Or
This
no?
equation includes any additional rebars that you put in the tension side with the pre-stress strength. this equation. And usually it's gonna be up to you to decide if you really want to add some additional conventional rebars with the pre-stress strengths. It's gonna be like a design thing. It's gonna be up to you. You know, sometimes you use number 7, another person's gonna be using number 8, right? So someone would like to use everything to be only pre-stressed. Someone else is gonna say, why don't we add some conventional rebars? Because this is gonna be, let's say, post-tension. You know, in post-tension, what do? You put conventional rebars, right? And then you pour the concrete. And then, of course, you put the strength in there, but you don't apply the tension force to it. And then, in some cases, you can strip the form. Just take all the formwork and all the shoring out. Now the beam is supported like this. Supported by what? It's going to be supported on itself. And it needs to have some conventional rebars, and there is no post-tension yet to it. You did not apply any tension to it yet. So some people would say, let me add enough reinforcing here so that the beam is going to be able to support itself, right? Now the beam is supported on the conventional rebars. And then after that, they start to apply here the post-tension force. So the beam now is kind of not 100% flat, it's going to be coming down a little bit. Now they apply the post-tension force. And then after that, they start to cast the concrete topping on the beam, the concrete slab. And then after that, they apply the live load. So in some cases, this reinforcement is going to be important for the design purpose because you designed it at the beginning so that you're going to be able to take all the shoring and all the formwork out. This depends on the way that you want to design it. Some people would say, no, I'm going to keep the formwork in there. I'm going to keep the beam short. I'm going to cast all the concrete. And then after that, I'm going to apply here the post tension while the beam is supported on the formwork. So in this case, the amount of rebars here, I can just add something for the shrinkage and for the cracking. It doesn't need to be a lot. So this is going to be fine. I mean, it depends on the way that you want to design your beam, if this makes sense. We're good?
Yeah,
Answer
thank
the
you.
question?
So when the formwork is taken out, the pre-stressed tension takes over?
It depends on your design. Give me an example, for example. Let's discuss it together. You have a concrete beam. It is pre-tension. What does it mean by pre-tension? It means that you have all the strengths in and tension before you bring the beam to the side. You take it there, you put it in place. The pre-stress is in effect now. They are working. They are supporting your beam. You add loads, it's going to be okay. This is going to be one case, right? Second case, post-tension. You decide not to add any reinforcing bars. Now you put the beam in place in the formwork. Can you take the formwork out? Can you slip it? Can you take it, strip the formwork? You cannot, because you need to apply the pre-stress force first. Otherwise, the beam is going to be unreinforced at all because you did not apply the tension force to it yet. So in this case, if there is no conventional rebars, you need to apply the post-tension force, and then after that, you can remove the formwork.
Okay.
Once you remove the formwork, now the beam is going to start to take loads. It's going to start to support the top loads.
Okay. Thank you.
No problem. One third case. You decide here to apply the post tension later. You don't want to apply it now. You'd like to wait. So in your design, you say, I'm going to have here a post tension, which means the tension is going to be applied after we cast the concrete. So we're going to bring the beam, put it in place, put some rebars, conventional rebars, to be enough to support the self weight of the beam. And then after we put the concrete, we're going to wait a week and then remove the formwork. Now the beam needs to support itself, and it has enough reinforcing bars to support itself. And then after that, we apply the post tension to it, and then you apply the loads.
Is that typically waiting the, was it 60 or 90 days or whatever it is for concrete to be the maximum amount of compressional strength?
Usually it's going to be 28 days, but there is additives like admixtures that you can add to concrete so that it can gain the full strength in 14 days or a
Oh,
week.
okay.
Yeah.
Alright.
This is not the only 3 cases that you may see. There's another case at which you're gonna put the formwork, put the reinforcing bars, this reinforcing bars, all right? Cast the concrete. And then apply some of this post tension. It's gonna be partially pre-stressed, enough to support the beam weight, and then strip the form. You just take the forms away, right? Now the beam is gonna be able to support its own weight with the help of this conventional rebars and partially pre-stressed. And then you leave it. You leave it for some time because you're still in construction. You don't really need the full pre-stress. And then you come later, you apply the full pre-stress force. So some strands gonna be tension, some strands gonna be just left for now. And this is usually the case in bridges. In big bridges, they do it this way. They do partial pre-stress at the beginning, just so that it's gonna be supporting itself. And then later on, they apply the full pre-stress force. So it depends on the design. You have here more control on the phases and the loading stages, if you like, to call it this way. You're gonna be controlling exactly how much pre-stress force you apply at what time of the loading schedule and staging. Any questions? No questions? All right. Now let me put this aside because we're going to be starting here to go through one example. We're going to do it next time, and now I'd like to speak on about your midterm. This is going to be through Proctoria, and I'm sure that you guys have gone already through Proctoria, right?
Yes.
Have you? Okay, good. All right. So you know what's Proctoria about. This may be open notes, but it means that you cannot use any software or any spreadsheet. Calculation needs to be handwritten, right? If you like to type it, or if you like to use a tablet, it needs to be proctored. So it's gonna be only the computer system that's gonna be proctored via Proctoria. This is gonna be the only thing that you can type on. Are we clear on this?
Yes.
Okay. So because it's gonna be a kind of a common question, can I use my, let's say, tablet? And the answer is, if this is gonna be the only equipment, this is gonna be proctored via Proctoria, this is gonna be fine. Otherwise, you cannot. It needs to be handwritten. Can you use a spreadsheet? Answer is no. You cannot use a spreadsheet. Can you use 2 computers at the same time? Answer is no, you cannot. Okay?
Professor, we can use the lecture notes?
You cannot use what? I'm sorry?
The lecture notes?
What's electron notes? I'm sorry.
Lecture notes.
Lecture notes, yes,
Yeah.
if open notes, you can use it.
So I can open the your lecture note and like take the equation or something.
Yes, you can print it, you can have it printed or have it on the same computer that you are using.
Okay.
Yes, if you like to print it, but at the beginning, of course, you're gonna be scanning your desk. So it's gonna be, I mean, any notes is gonna be okay. Any notes from any place is gonna be okay.
Okay.
All right. Did we cover all questions or issues related to Proctoria and taking the exam?
Wait, sorry, so the Proctoria lets you open like PowerPoint and because I have mine like on notes.
Yes.
That's you? Okay.
Yeah. In the settings, I can make Proctoria not to let you go between files. But what happened, Proctoria is gonna be recording everything that you visit. If you open any file, it's gonna show exactly what you have opened, right?
If we want to use our iPads to write down the exam, does it also have to have Proctorio on?
Yes. So in this case, I would suggest that either that you do it on your computer or you do handwriting.
And what if we have our notes on our iPad? Did you want us to
So
then
the
move them to the
iPad, when you
computer in
need
that
to
case?
register, so in this case, you need to log in with your iPad and have Proctoria work on it. Or proctor you through it,
Okay, thank you.
no problem. I guess I covered all issues related to taking the exam itself. Now, someone's gonna say, if I'm gonna be doing here this handwriting, when I'm gonna be taking the exam, I need to scan it and upload it, right?
Yes.
So I'm gonna give you some time for that. I'm gonna give you 15 minutes. But this 15 minutes not to be used to solve the exam. This 15 minutes only for scanning. So I give you here enough time so that you can upload your file with the answers.
Okay, Professor, I use my phone for scanning. So I will let you know when I'm done with the exam. I will start scanning because for sure Proctoria will record me when I am using
Yes.
the phone.
This would be fine, absolutely. So once you come to the end, right, you're gonna stop working and be sure that the camera is recording you while you're taking the picture of your exam. This would be fine. And don't forget that once you scan, you cannot go back and start to solve, right? It's gonna be at the end.
Yes, for sure.
Okay, all right, so let's get very clear. All right, now let's talk about the exam. What's gonna be there, right? I'm gonna be looking at this. I'm trying to understand what happened here. I mean, this is gonna be like the core of our business. You're given here a beam, and then you have a section in the middle and at the end. So let's say that I'm looking for some beam that I'd like to work with. I'm not gonna bring a rectangular section. I'm gonna bring it something like this. So what do we have? You have the concrete strength. I have a question here from Kyle, and it is good that we discuss it. I want to cover all questions, so no one's gonna be left behind answering all the questions. And then you say the camera is gonna stay on your desk. How that works? Proctoria is gonna ask you to do scan for the room. Have you seen this before?
Yes.
Yes.
Okay, can someone explain, because maybe some of you guys didn't see it yet. Can someone explain, please, in simple words, what's gonna happen? I personally have not taken the exam with Proctoria. So someone who has taken it needs to explain us how it works.
So last
Oh, go ahead.
semester, when I think it was for your CO class, Professor, Proctorio did the checks and then it made us move our computer around to see what was in the room. But what was really annoying about that was that it would stop in the middle of the exam and it made us do that multiple times.
Multiple times.
While we were taking the exam.
Yeah. I see.
So I don't know if it's possible for you to only do it maybe like one or two
beginning.
times, but multiple times. Yeah, it's kind of annoying when you're taking the exam.
Well, I'm gonna give you enough time so that if Proctoria is asking to scan the room, you're gonna have enough time for this and you're not stressed out.
Okay, sounds good.
All right. Still have any questions, Kyle? We're good?
So that means we have to do during the exam, we have to do scanning multiple times the area?
Yeah, it may ask you. Usually I understand that it does it in the middle of the exam, one time.
Okay.
So it's gonna be only once. This is my understanding. Unless the
Okay.
exam is gonna be long enough, and in this case, it's gonna ask you to do it a few times. But it shouldn't be a problem. I mean, you guys should be fine, I guess. I mean, you have open notes, right? So what? The only bad thing that that maybe you're gonna be communicating with someone else, and Proctoria is gonna be watching this, so you should be fine. I don't think that you really need to talk to anyone while you have all the notes.
Professor?
Yeah.
Do we still need to log in through Zoom during the exam?
It's gonna be up to you. I'm gonna be on the office time, not the office time, excuse me, the lecture. Zoom meeting. I'm gonna be log in. Just in case if you have question, I'm gonna be able to answer.
Okay, thank you.
No problem. So let's look here at this given section. What is the information available? What is the information that you need to learn about? During construction here, what they do, they put the double T first, right? So in the fabrication yard, in the factory, you don't have this concrete topping, right? You just have this, the light double T. This shaded 2-inch, this is gonna be additional topping. And this is why we have on top properties and then you have top properties. For the on top properties, the total depth here is 24 inches. You have the concrete strength, you have FPU. You have the total cross-section area of this double T is gonna be given to you. So you don't need to do any calculation for the properties because it's gonna be given to you, like the steel sections, right? You have the moment of inertia, you have Y top, you have Y bottom and Y top, you have SB, which means section models for the bottom and the top, and then you have the weight. This weight 359 P left is gonna be the weight of this double T. Like this gonna be the dead load. Someone's gonna say, how about this top properties? You can say, yeah, top properties, I guess I don't have cross-section area for it. And this could be a big question mark here, right? Why don't they give me here the cross-section area with the topping? I have the moment of inertia. And you see here it goes up with the top properties, right? Why bottom is going to increase? Why top is going to get reduced? Why? Because you are pushing here the neutral axis up. Same thing here for S bottom and S top. It just goes up. And here's the weight. This weight here includes the weight of this concrete double T and the topping. Are we good about this? Yes? No?
Yeah.
Okay, good. Difference between these two numbers is going to be the weight of what?
Concrete.
The weight of the topped concrete.
Up.
Right. So if I'd like here to subdivide this into two separate sections, I'm going to say how much is a dead load? I'm going to say dead load equals to what? I need your help. Dead load equals, the self weight equals how much?
It's going to be the area times the unit weight, correct?
Yeah, this would be great. But why would you spend the time and redo this again and it's given to you right here?
Just to double check.
No, don't double check. This is going to be consuming your time in something that is not really needed, right? So let's try to minimize here the amount of time that you spend on other stuff that's not really needed. Someone's going to say, do I really need to do, again, the moment of inertia or this cross-section area? I'm going to say, no, it is given to you, just use it. Okay, so how much is the dead load again? The self weight, how much? I need someone to read it for me.
Just 609 pounds.
I'm going to say the dead load, the self weight of the structure itself. How much is this?
Well, if it depends
59.
if it's
359 P left.
if it's a
I was
foot
gonna say,
long.
why it is not 609? Yes, say because the 609 is going to be superimposed dead load, right? Sometimes written SDL or sometimes written as ADL, additional dead load. How much is this additional dead load? I'm going to say 609 minus 359. How much is this? Can someone help?
60.
How much?
360. Sorry.
360?
250. I got 250.
250.
Yeah, 250.
250 pound per linear foot. I guess now you know how to find out the superimposed dead load. How did you do it in the past? Did we have it here? We just added the superimposed dead load and the live load in one piece here, in one shot. We say it's going to be 0.4. But we didn't know where it's coming from, this superimposed dead load, the additional dead load. So in here, I'm telling you that the self weight of the beam, which is a dead load, is going to be 359. The additional dead load is going to be the difference between the top and the untopped. Are we clear on this?
Yes.
100%. I don't want a question to come. Someone's going to be saying, I don't know the difference between this and that, this additional dead load or superimposed dead load. Now you know about it because this is going to be the weight of the untopped for this only, this light or this white section. And the weight of this additional concrete topping is going to be the 250 P left. Right? If I tell you here, life load equals 50 pounds per square foot, can you tell me how much is this life load in terms of P left? Pound per linear foot. Is this the span of the double T or the span is going to be in the other direction, perpendicular direction to the screen? I'm just wondering. Where is the span of the beam? Is it 10 feet?
The
Or
span
this
is
be the
10
width?
feet, and then the length is however long the double T goes.
So the length is going to be like perpendicular to the screen, right? And this is going to be the width of it. So when I say here life load in terms of pound per linear foot in the longitudinal direction of the double T, I'm going to say it's going to be equal to 50 PSF times 10 feet. Now you know what I'm talking about. I have taken this 10 feet multiplied by uniform load is going to be 500 P left. Does this make sense or no?
Can you explain that one more time?
Okay.
Sorry.
Uniform load is given as 50 pounds per square foot. This is going to be on the plan, on the big plan of the double T. This is not the span. This is going to be the width. So I'm going to write here, right? The width equals to 10 feet. From where? From here. I'm not going to tell you the width is going to be equal to 10 feet. I'm just going to give you this picture and this information. And then, of course, not for this exact section. I'm going to change it. But you need to figure out the self weight, the 359, the additional dead load, the difference between the two, and then the life load. If I give you the uniform life load as 50 PSF, I'd like to figure it out in terms of P left of the longitudinal direction of the double T, perpendicular to the screen here. So I need to take the width multiplied by the uniform load. So 50 is going to be the uniform load as PSF, pound per square foot, multiplied by the double T width. With that, I'm going to have 500 pound per linear foot.
Okay, thank you.
No problem. Is everybody here clear on dead load, self weight, and life load calculation for a double T like this? 100%. Yeah. All right, very good. Now I need to put this back. You say, okay, so what happened here? I said, determine the effective pre-stressing force needed to balance maximum of 90%. Do you guys have any questions on this? I'm gonna do it exactly here. It's gonna be to balance something of the self weight of the dead load, right? Because what is a dead load? Dead load is gonna be the self weight of the double T only. Now we're talking about fabrication yard. So I guess you guys know how to do this now, correct? Any questions on this? How to do the balance load? How to apply certain amount of strains to find out the balanced load, right or wrong? And then after that, how many strains you need to provide? And of course, number of strains needs to be rounded down. Why? Because it says here maximum. You cannot go beyond this limit. This limit, let's say I can propose maybe 87%, maybe 85%, maybe 99. I can just put a number there for you, right? So you should expect something like this, and like this, and also like this. Initial pre-stress. Now, if you know the actual number of pre-stress, the pre-stress strength, you can figure out the initial. Just take the number, multiply by 0.153 cross-section area, right, for one strand times 189 KSI. Now you have the initial pre-stress force. When you apply the pre-stress force, would you have the topped or untopped section? This here pre-tension, right? This can be done in the fabrication yard. Would you have the topped or untopped properties?
Untopped
Untopped. Why?
because it's being fabricated.
It has just been fabricated, right? When do you think this topping is going to be applied?
At the work site.
Yeah, this is after you take this double T, you put it in the building, on the top of the beams. Now it's supported, and then you put some reinforcing for this topping, and then you pour the concrete. So at the time here of pre-stressing, you don't have the top properties, and this give you the properties that you need to use in your analysis, right? So check the stresses, top and bottom, right? All of that is going to be based on the on-top properties. You guys agree or no? Or it's not really clear?
Agreed.
All right, great. Now, the beam, we're going to put it, or this double T, we're going to put it in place. It's going to be spanning between two beams, right? So in plan, if you think about it, this is going to be the double T, and then we're going to have two beams. It's going to be supported on these two beams. The pre-stress force, if you remember the equation, the equation for the stress, top and bottom. Just, I want to get to it. Slide set doesn't really include what I'm looking for. Went through all of these equations, right? For this stress equation, F top and F bottom, if you recall this F top and F bottom, right? F top and F bottom for the dead load only. We have done this only for the on top. Now the pre-stress force is already there, right? This PI and PE, we did this already. And look which AC should I use here. It's gonna be the on top, correct? It's gonna be this one, 449. After we put this double T in place, supported by beams, we're gonna put this load. Now I need to check again the stresses at the service stage, right? It's gonna be based on this. Which AC should I use now? Should I use the topped or untopped?
Topped.
Great. But when you apply the pre-stress force, it is already locked in the double T only without the topping. So actually you cannot, because the cross-section area exposed here to the compression is gonna be only this light area. It's gonna be the untopped. And this explains that there is no top properties for the cross-section area, because you cannot apply the pre-stress force to this shaded area. You applied already to the double T, and the double T has taken this already, and the stress is locked in. You have all of this compressive stresses already into the double T without the topping. When you put the topping now is not going to be taking any stresses from the compression, from the pre-stressing. Does it make sense?
Yes.
Yes.
I want to be sure that everybody understands what I'm saying here. So if it is not clear, just say repeat. Or should I just repeat anyways?
Can you repeat it one more time?
Okay, here's the double T. All right, it's gonna be this piece here. I put the pre-stressing force already in there. Okay, start to camber. I move it to put it on the beams, on the side, on the construction site in the building. Then I'm gonna put some concrete topping, right? Now, the axial force that I put here in the double T, these things are gonna get transferred to the concrete topping, even though that I casted this after the fact. You say, no way, because the stress is already, it's gonna be in the double T only, not on the topping. Top is not gonna see any of this compression force. Topping is gonna see the additional moment effect on the stresses. It will never see the axial compression on the double T. It is already there. It is inside the double T itself. Let me tell you this differently. Here's a double T, right? You have certain amount of pre-stress, and you calculate the stresses top and bottom based on the self-weight and based on the axial force, the pre-stress force. So the stresses are locked in now. Let's say that you are going to keep it in place. We're going to keep this beam in place. We're going to provide some support to it, right? Now add some loads from the top. Now the beam is not moving because I decided just to keep it in place. Something that we usually don't do, but I just decided to keep this beam in place or double T in place. Now, this additional concrete topping is not doing anything to the beam because the beam now is short, supported. Now, this concrete topping is not going to see any additional stress because the stress from the compression force from the pre-stress strands is already into the double T without any topping. So adding the topping here, or this top cross-section area, which is 2 inch by 10 feet, is not going to be really exposed to any compression force from the pre-stress. The pre-stress force is already taken by the double T. Does it make sense or no? Not clear, not very clear.
It makes sense. Thank you.
Okay. So when you check the stresses at the initial pre-stress at PI and use the self-weight, you're going to be using these properties. When you check the stresses at the surface life, you're still going to be using this 449. But for the additional load above the dead load, which means superimposed dead load and live load for both of these two loads, right? The effect of this additional loads, you can use this top properties. Yeah, no? Meaning, when I use this equation here, for PI and dead load, this is gonna be okay. I mean, I have no problem. I'm gonna be using this properties on top. I'm gonna be using for the dead load, I'm gonna be using 359, which means a self-weight. This before, right? I move this item to the construction site. It still is gonna be the fabrication yard. So this equation is good, right? If B is gonna be PI, AC, yeah, it's gonna be all of that on top. Forget about the topping, because all of that is gonna be done in the fabrication yard in the factory. With dead load here is gonna be this 359 is gonna be the self weight of the beam or the double T. Now I'd like to do this. How can I do this? I guess PE is gonna be the new PE, right? After reduction of the load. AC is gonna be this old value. Now the effect of this M total is gonna be not really M total in this case, right? It's gonna be only additional dead load plus life load is gonna be in this equation. And the original stresses that you calculate out, top and bottom, is gonna be locked in. It's becoming more complex, this pre-stress thing, or still okay?
So
Little bit.
I have a question. So when we're checking for the final stresses, you say we have to use P effective, right?
Yeah.
For P effective and for the final stresses calculation, we only need to use the top part of properties, or we have to add it to the untop.
Okay. Let's say when you move this double T, I'm gonna take it here on the stages, right? First stage, you have this in the fabrication or in the factory. And then you'd like to check here FPI, which is this one here, right? If top and bottom, right? What properties would you use? Top or on top?
On top.
On top. And they're gonna be using PI, right?
Yep.
Now let's move to the construction side. Now we install this double T in the building. All right. Which amount of force that you're gonna be using? PI or PE?
P.
PE. Good. Now you put it in place. Did you add the additional dead load yet? Let's say, no, not yet. I didn't cast the concrete topping yet, right? Did you add the life load yet? I'm gonna say no, we didn't add any of that yet. Correct?
Yes.
Still one stage, I just moved it, I put it in place in the building. Now I'd like to see what's gonna happen in this stage. Can I use this equation? You say yes. What P force would I use, PI or PE at this stage?
PE.
PE. Would I use dead load or dead load and superimposed dead load and life load?
All of them.
No, I said I didn't apply anything yet. You remember?
Oh, my bad.
Yeah. We said that this is gonna be right once you move it to the side. I'm gonna put this in the building, right? I have a couple of beams. I'm gonna just put this in place. Do I have dead load, additional dead load yet? Do I have concrete topping yet? You say no, nothing yet. All right. So I'm gonna take it, put in the building. What loads do I have applied on it? I'm gonna have here PE as a compression force, pre-stress. And when it comes to the applied load, I'm gonna have only self-weight. I didn't do anything yet, correct? So this equation seems to be good, but instead of PI, I'm gonna put here PE. And my question, I'm gonna say very specific. I'm gonna be very specific here in my question. I'm gonna say, once you move the double T, and before you apply the live load and the concrete topping, right? Find out the stresses. In this case, you're gonna say here, PE, and it's gonna be only M dead load, correct? You agree on this? We're good?
Yeah.
All right. Now we have the stresses top and bottom. Which top is giving the top of the concrete topping or the top of the double T? Just want to be sure.
Double T.
Double T. Why not the top of the topping concrete? Because concrete topping is not there yet. We didn't put it yet. I'm talking here about the stage at which I just moved the double T, put it in the building, and no concrete topping yet. So what loads do I have? I have here PE, and I have M dead load. And the stress is going to be right here at 24 inches from the bottom. And the stress is going to be right here at the bottom. We're good? All right, now let's add the concrete topping. Now the stresses that you have just calculated out, when we move the double T to the side, it's going to be locked in. What do you mean by locked in? It means this calculated stresses is going to be based on the on top properties, and you're going to have a stress top and bottom, which means right here. Let me zoom in. It's going to be right here at this point and at that point. You have it already based on this given properties, the on top. Now what you need to do is look at the additional load that you're going to be adding. What additional load? I'm going to say additional load is going to be this 250 plus the 500 in this case. So my total additional load, including what? Additional dead load plus life load is going to be equal to 250 plus 500 equals 750. 750 what? P left. This additional load, which means additional dead load and life load, is going to be coming on these properties. You're not going to be coming on this properties on top, right? Because when you apply this additional dead load, total additional dead load, including additional dead load and life load, they're going to be coming on a new section that's already hardened. It includes concrete topping and a double T. Yes or no? We're good? Not really? Let me draw it here for you. Here's a double T or the beam, and here's the concrete topping. I'm going to make it this way. Okay? I'm going to say, I'm going to draw here some lines so that we know which section we're talking about. Let's give you my vertical datum for the stresses. Let's give you right here. And before I do any topping, I'm going to say the stress looks like this. Okay? This is going to be here F bottom. And this is here is going to be F top, which is this value right here. So this load combination or load stress distribution is going to be based on what? Let me write this down. It's going to be based on PE and on top properties. Does it make sense now? Going to have a stress top and bottom of the on top section. This is going to be the concrete topping. Let me know if this makes sense what I'm talking about.
Yeah, it makes sense.
Now this is going to be the concrete topping, right? And what load should I use here in this case? I'm going to say dead load only, like self-weight. In our simple example that I just showed here, this is going to be the 539. So your dead load is going to be based on the 539, right? So I'm going to say this is going to be for the 539 P left. So what I was just talking about, right? It's going to be based on PE and on top properties. And we're going to be using here 539 as the dead load. That's it. We're done here with the second stage. So the first stage, what was the first stage? I'm going to say at the fabrication yard in the factory. It's going to be based on PI and dead load, the 359. It's going to be phase 2 or stage 2. You see here, this is going to be stage. All right. Should I draw here stage 1 just to complete the picture? What do you guys think?
Yeah.
Yes.
So I'm going to say, what is the stage 1 again? Stage 1 is going to be at the fabrication yard, right? And just move it here. I'm going to put it right here. It's going to be stage 1. The stage 1, I have PI. And they have on top, right? And they have dead load of 359. We're going to check here the stresses top and bottom. All right. And this is not feet. This is going to be F top, right? And F bottom. Just to be sure that we're not confused about this. So what's going to happen in stage 3? In the stage 3, I'm going to be applying the addition dead load and life load. So I'm going to say, okay. So I'm going to put here stage 3 is going to be right here in this place. I'm going to put it here. It's going to be stage 3. I have used already this PE with the dead load. So I need to take the stresses from here. You see the stresses here from here, this stress distribution. Now I need to add to it. What I need to add to it is going to be the effect of the additional dead load and the life load. But when I bring this effect of dead load on life load, I need to use here PE in my equation, which is this one, instead of M total, because now this PE has been taken by what? But the stress is going to be included here. And the stress is going to get locked in the concrete beam itself. So this is stress, I'm going to call it here F bottom. I'm going to give it here a symbol. I'm going to say here 2. What is this 2 for? Because it's stage 2. And this is going to be F bottom. It's going to be sub 2. This makes sense? You know what? Let me make it like this. Just for simplicity. And this one, I'm going to make it 2 like this. Because it's going to be really tough to work with Adobe and put subscript and superscript. So I'm going to say it's going to be 1, right? Stage 1, you have the stresses. We check the stresses here for PI and dead load, and everything is good. In stage 2, I'm going to be doing here F top 2 and F bottom 2. It's going to be based on PE and 539, which is only dead load. Now it's stage 3. In stage 3, I'm going to be taking the same stress value here. Right? Going to be taking the same stress value. It's going to be right here. And F bottom is going to be the same value here. Now I have additional dead load of 750, excuse me. Of 750 P left. So this, the new load that I'm going to be adding here, additional dead load plus life load, is going to be equal to 750. I'm going to have also this PE. So because I have this PE and the self weight is already locked in, I'm going to be just taking this stress. Now I need to add to it a new component. And this new component is going to be coming from the additional dead load and the life load. So take this new load and use this equation. And all what you need to do is just use this M divided by S, because now you're going to have a new moment coming from this addition dead load and life load divided by the section modulus of the top properties. What are the top properties? What is that? Going to be based on these values. If you remember these values, it's going to be based on this top values. Therefore, I don't need A because A was already used in the compression force. And the stress is due to the self weight is already locked in the beam itself. Now I need to take this additional load divided by S top and bottom, which is top and bottom for the top properties. So I'm going to say it's going to be the top properties.
Professor, the dead load for first stage is 359, right?
Yeah. It's right here.
Okay. Okay. Thanks.
359 is right here. From here. Okay.
Right.
You wrote 539.
What? I'm sorry. It's my
On you dead load right there. Yeah, you wrote
It is
539.
my mistake. 359. Thank you. Thank you very much. 359. You're absolutely correct. 359. But additional dead load, as we calculate that, is equal to 750. So this one is correct, right? Okay, good. Now, this is stress. The top and bottom is locked in, the two values, right? Now I bring here new load, and then I can find out the moment due to this additional dead load and life load divided by S top and bottom for the top properties. Now the question is, how can I add it here? Right? Any idea how do you add this? the stresses, both top and bottom, is locked in. Are you guys following me?
Yes.
Now, when you're adding new stress to it, and here's the new stress, you're gonna say, let me find out the moment, right? Divide by S, and this is gonna be my new distribution of stresses. Let's say it's gonna be this line here. And I can do this in different color. Let me do it here in blue. Let's say any two values that you're gonna be getting here, top and bottom. What should I do with these values? Are these values, should I just look for the maximum and just use it, or what should I do? I'm gonna say no. This new values can be additive to the existing values, right? So this can be existing values. If top for the second stage, if bottom for the second stage, I need to take him and then add new values to him. So I'm gonna say, let me take this, and now let me look at the top stresses. The top stresses here is not gonna change from this blue pile or blue values, right? It's not gonna change. The bottom stress here is gonna be equal to the originally developed stresses F2 plus the new value. And here is a new value. If I may zoom in here, I'm gonna say this new value from this point to that point, right? This new value from here to there, right? Which means the stress at the top of the beam itself needs to be added to the stress which was right there, which was this one, right? In stage number 2. Let me throw some numerical values so we're clear on that. Let's say F top, the number 2, I'm gonna put a value here. I'm gonna say, let's say 200 psi. Just throw some values so that we're clear on what we're talking about. And this bottom values, I'm gonna say, it's gonna be about, let's say, 100 psi. No, not 100. It's gonna be much higher, right? According to this scale, this is gonna be 400 psi. All right. Just because the effect of this additional dead load on life load, when you divide by S top and bottom, there is no axial load effect here, right? For this distribution, and we can do this as, let's say, in here, I'm gonna have additional of 250 psi, and this is based on M over S, and M, of course, due to only additional dead load on life load, M over S is gonna be equal to 250 psi at the bottom. And on the top, I'm gonna throw there a value. I'm gonna say, let's say, which is this blue ordinate, right? It's gonna say maybe 100 psi on the top. And where is gonna be in the top of the concrete topping, of the top of the beam itself. On the top of the concrete topping is gonna be slightly higher. So I'm gonna make it here as 125. Okay. So where is this 125? Is gonna be from this blue stress, is gonna be from here to there, right? And where's the 100? The 100 is gonna be from this point to that point. Are you good about this or not really? So the stress from this value, from this point to that point is gonna be 125. Cool. Are you good about this? So the stress for the blue distribution here, right, and all the way in the top is gonna be 125, right, and the top of the beam is gonna be 100, right? Now I need to look at the final stresses. Final stresses is gonna be the addition of this blue distribution to the red distribution from stage number 2. So all the way in the top, I need to find out the value, right? Are you guys with me? Any questions? Any questions? No?
Just about the exam, how many problems are we doing?
One big problem,
Okay.
but it's gonna include lots of work.
And Professor, you said it's gonna be just T-beams, right? No rectangular? Just double T-beams?
What do you mean? I said it's gonna be something like this, right?
Yes.
Didn't I say it's gonna be something like this?
Yes.
Okay, so what rectangular beam are you talking about?
I mean, just the regular beams that we did for the homework. But it's just gonna be like this.
Like this.
Okay. Okay.
Are you here? Are you with us? Guys, are you clear on what I've been talking about here for the past like 45 minutes?
Yes.
Yes.
Okay, good. You understand the difference between on top and on top properties. You know that you're not going to have a rectangular beam in your exam, and you know it's going to look like this, and you know how to figure out the self weight, and you know how to figure out the additional dead load.
Okay.
Am I correct? And the life load. Is everybody following me on this?
Yes.
Yes.
Otherwise,
Yes.
it's gonna be, I mean, it's going to be a big issue during your exam if you don't know all of that. Okay, good.
But to be honest, after that here, I get confused.
What do you mean? After this?
Like when you see this one, it's all good.
Okay,
But
good.
then when we start the other one, I
The
get
stress
confused.
distribution, right? Okay, good. Just stay. Hang on with me. Stay. It's not an easy thing. It's not something that you can just do it in a minute. Okay.
Okay.
So we said that here we're going to have 3 stages of loading. All right. We're good about this. You understand that we have 3 stages of loading. Am I correct?
Yes. Yes.
Okay, good. The stage number 1, you're at the fabrication site. You're at the factory, and you have PI applied, and then you have on top properties. We're good about this. What is on top properties? As I said, you're going to be taking it from here, right? It's going to be this one. We have top and on top properties, correct?
Okay.
Okay, so it's going to be based on top properties. It says here very clearly, stage 1 at fabrication, at the factory, you have PI, and then you have the on top properties. And the weight is going to be the 359 according to this simple example that we are given, right? According to this. Okay, good. So are we good about the stage 1 to everyone here listening to us? Yes or no?
Yes.
Yes.
100%. 100%. I mean, I need to have response from everybody, please.
Yes.
I want this midterm
Yes.
to be good with you guys, and you're gonna be good with it, you know?
Yes.
Okay.
Good.
Stage number 2. I took the beam or the double T or whatever structural element, I'm gonna put it there in the building. I didn't cast yet the concrete topping. It's not there yet. There is no life load. This is gonna be the second stage. Now, the pre-stress force is gonna drop from PI to PE, correct? Yes?
Yes.
Okay,
Yes.
good. Do I have the concrete topping yet?
No.
No, it's gonna be on top.
No.
I didn't cast any concrete. Now I need to check the stresses. The stresses here is gonna be based on PE and on top properties. Someone's gonna say, what on top properties again? I'm gonna say this on top properties, right? Now we're done with this. Now we know stage 2, right? 100% of the people, yes or no?
Yes.
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 Good. Now the stress, all the stresses now are locked in. The beam has taken now this beam or this double T, right? Excluding the topping is not there yet, has taken the stresses from the pre-stress force. The pre-stress force is gone. I cannot touch it anymore. It is gone. Now I need to go here to phase 3. Phase 3 here is going to be based on the top properties. Now I have a new section with some new topping, new properties, right? New moment of inertia, new Y top, new Y bottom, new S top, new S bottom. Now I'm going to be adding this additional load of the 750. Do you guys know where's the 750 coming from? Just in case, it is from here. It's going to be the additional dead load and life load. Now I said, okay, let me bring here this additional dead load and life load, right? Let me find out the moment for this additional dead load and life load. Now, when you apply this additional dead load to your equation, you cannot include the dead load because you include this already in the locked-in stresses and in the PE equation because the PE already has been taken by the on-top properties. We're good about this? Meaning the stress here, top and bottom for this blue distribution for stage 3 is going to be based only on M and S. No pre-stress equation in here in stage 3. Now this stresses, the blue stresses, is going to be in addition to the locked-in stresses that you have right here. Now I need to add this blue distribution to the red distribution. Meaning, let me look here on the top. How much stress that you have from the red distribution here, all the way in the top of the concrete topping? How much was the stress?
100.
0. Should I repeat the question again?
Yeah.
Yes.
How much is the stress at this line in stage 2? There is none because the concrete topping was not there, right? At this stage here of loading, did you have any concrete topping? No. Did you have any stresses in the top of the concrete topping? No. So the stresses at the beginning was equal to 0. I have only 2 stresses in stage number 2. I have F top, which means top of the beam, and F bottom of the beam with no topping. And it was equal to 200 here, 400 at the bottom. The stress all the way in the top of the concrete topping was equal to 0 in this case, right? It's okay. How about the stresses due to this additional dead load and life load? All the way at this line here. Do you know this value? How much value did you get here? Can you
From
look
where?
here?
From where, Professor?
I'm saying here from the blue distribution, from stage 3, from M over S only. How much is the stress at this point?
125.
125, thank you. So total of 125 PSI, where? All the way in the top of the concrete topping. How did I get this again? 0 stress here, and 125 here from just M over S. I said, okay, good, all right. How about at this line here? How much is the stress right here at this point, right? From stage number 2. How much was the stress here? Can someone read it for me?
100?
200, isn't it 200?
Yeah, 200.
Yes.
From here. And how much is the stress from the blue distribution?
100.
100. Total of 300 PSI. Again, where is this coming from? 200 from stage 2 and 100 from just the additional M over S. Let me try this at the bottom. How much is the stress at the bottom from stage 2? Can someone read it for us?
400 PSI.
400. And how much is the stress? The blue distribution just from M over S.
250.
250.
250.
Total of 650 psi. Now, how the distribution is going to look like? If I'm going to do here a vertical line for the datum, look how it's going to look like. And the top is going to start here, somewhere here, right? Let's say it's going to be like this. It's going to come like this. It's going to come like this. Distribution is going to be like this. See this red distribution, new one? Going to make it different color. And this light blue thing. Does it make any sense to anyone? Yes or no?
Yeah, it does.
Yeah, it's making sense.
Yep.
So again, I'm splitting here the stress source. I said here, I'm going to repeat the whole thing again. You just I have here 3 stages, and based on each stage, I'm going to split the stresses. So I said at the beginning, I'm at the factory. I have PI, and I have only dead load, self weight of the beam. I can check the stresses top and bottom and compare it with the allowed stresses. And you guys know how to do the allowed stresses, and you have seen it already. Second stage, take the beam or the double T, put it in the building at the side, put it in place. Don't do anything to it, just put it in place. Let it support itself. Determine the top stresses and bottom stresses. Now, the amount of force that you're going to have in the strand is going to be PE, it's not PI anymore, right? And you still have no top properties. You're going to be using the on-top properties. And based on this, figure the stresses top and bottom. Now, what does it mean by bottom? Bottom is a bottom. It's going to be only one bottom. Top, it means top of the beam itself with no topping. This guy is not here yet, right? He didn't put it yet. And let's say for argument's sake here, and just for the sake of discussion, I'm going to put here the bottom stresses for stage 2 is going to be 400. The top is going to be 200. Now, what does it mean by the top? In this case, it's going to be this line. Do you have any stresses at this point yet? You see, no, because I don't have any material yet there. There's no concrete. I cannot just extend or extrapolate the stresses. It is not there yet. Now I'm done with this, right? Are we good about stage 2? Everybody? 100%?
Yes.
Yes.
100%.
Yes,
Do
sir.
you have any questions asked? Go ahead. I hear start of a question and then stop. Go ahead, please. Any questions on stage 2?
No questions.
Great. Okay. So stage 2, again, you put the beam in place on the side and you didn't load it with any topping. You didn't do anything to it yet. Now the stress is going to get locked. What does it mean by stress is going to get locked? The stress in this beam here is going to stay as is based on the pre-stress force. When you add any topping to it, this topping is not taking this pre-stress force. It will never take it because the beam is already taking this. Now you come here and then you add the topping. What's going to happen? It's going to be like additional weight. Also, at the same time, section property is going to get changed. What do you mean get changed? It's going to increase. Look at this. Look at moment of inertia. Look at S top and S bottom. They're going to go up. You see, okay, good. But this new properties is going to be only supporting the new loads that you add to the beam, including what? Let's say including this new loads that you add to it, including the additional dead load and the life load only, because the self weight and the pre-stress force is locked in the beam without topping. So let me take here the stresses. It's gonna be 200 psi, which is this red one, and there's gonna be 400 psi at the bottom. Now let me add the new stress distribution to it. Now what's the new distribution? It's gonna be this blue line. This blue line is gonna be stage 3 partial. It's gonna be based only, this blue distribution is gonna be based on M over S. M due to what? Additional dead load and life load. S is gonna be S top and bottom for the top properties, for this properties here. Okay, good. Now what should I do? Now I need to take this red distribution to this blue distribution and add them to each other. Now you have two distribution of stresses, right? Just add them. So how do you do this? You look here at 3 lines. Here's the top, very, I'm gonna say here, very top. And this gonna be the top of the bare concrete with no topping, and the bottom of the concrete beam. The stresses here at this line, in the red distribution, there is nothing. When you look at this, nothing is here. Just gonna be equal to 200 psi from here to there. Now, how much you need to add to it is gonna be this 100. And this gonna be based on the stress distribution due to M over S at this point. How about all the way in the top, the very top? It's gonna be based on only M over S, because the pre-stress force and the self weight is not gonna go there and put additional load on the top of the concrete topping. It will never do this, because all the stress is already locked in for the P and dead load. So here, let's say it's gonna be 125, right? So I'm gonna be taking 0 plus 125 is gonna be equal to 125. Top of the beam itself, from this side or from stage 2 is gonna be 200, plus additional of 100 from the blue distribution. Now I'm gonna have a total of 300. All the way at the bottom, I'm gonna have here 400 psi, plus additional 250. It's gonna be 650. So all the way in the top, this is gonna be the amount of stress. Only is gonna be this value. The 350, the 300 is gonna be from this point. Do you guys see my the cursor?
Yes.
Okay. So where is this 125? It's gonna be from here to there. The 300 is gonna be from this point all the way to that point. There's gonna be a big change in the stresses. Why? Because you have some locked stresses plus some new stresses coming to it. The bottom is gonna be 650. Questions? Is it clear now?
Professor, I'm just confused about like how we got three values.
Which one?
I'm confused about like how we got the 3 M over S. I know we used like
this one here, M over S.
The section modulus. So
okay.
that one right there, the 250, that's for section modulus at the bottom.
Yeah.
Like the section modulus at the bottom, and then for
but
the
top properties is gonna be based on the top properties, right? So when you have here this S top, in this case, is gonna be this S bottom is gonna be 1535, and S top is gonna be 5761.
Okay, so for the top, the 100 and the 125.
Yes.
How it like?
Same thing.
We only have one section
Same
modulus.
thing.
We use the section modulus in the top.
Yes.
But how do we get the actual 2 values?
The actual 2 values, I'm just throwing number there. This number may not make any sense to anyone if you run actual values. I'm just throwing numbers there so that you know you're gonna be adding this to that instead of solving it in symbolic, like symbolically, if you like. I don't want to answer it in symbols, so I'd like just throw some number there. So don't try to find out the values. These values are just there. I'm just throwing here values for sake of discussion.
Is basically gonna change due to the M and not the S on the top. It's because I think what he's confused on is since there's 2 MS values on top.
I cannot hear you well. Can you please speak up?
Oh,
I'm sorry.
my bad. I said it's basically I think what he was talking about, since there's two MS values on top, he was confused on how we got them. And then the S values, they're
This
the
is
S
gonna
top
be S
value.
top. This is
They
gonna
don't
be.
change.
This is not gonna be really M over S. This is gonna be M over I, MC over I, right? And this is gonna be to one top, right? This is gonna be M over S top. This is gonna be M over S bottom, because I'd expect that you know the equation, how to use this equation, right? And this is not gonna be really M over S, right? This is gonna be M over I times little bit of y here, and this y is gonna be the distance from this center, right? All the way to that point, right? So it's not gonna be really M divided by I times C. It's gonna be M over I times Y.
Oh, okay. Yeah, that's what I was confused about.
Is that the confusion? Okay.
Yeah.
I hope
Okay,
that was
thank you.
clear. And if you have any issues, you still can go back to this slide set that I added in the past, and you can find out the stress based on this equation. If you remember this equation, right? Sigma at any point is going to be equal to M times Y divided by I. And Y in this case is going to be the stress at any line. In this case, here's the Y distance from the neutral axis to any point of interest, right? This is going to be Y. Moment of inertia is going to be I, and the applied moment is going to be M. And this is exact same equation, right? Same concept here. Nothing is new. I'm just saying that this is going to be based on the concept of M and S. It is not really going to be based on this pre-stress force. More questions? In Dana. Dana, you have a question?
Oh, no, Professor, I'm good. Good.
Okay, I'd like to hear it from everybody, please. If you have questions, ask me.
No question.
Should I call one by one? Chris, Amar, RJ, Basil.
No questions.
Okay.
Yeah, I said no question.
I'm good, Professor.
You explained it too well, Professor.
Until now, I'm good, Professor. If I need help, I will email you.
Okay, I want to be
Wait,
sure that
how much time do we have for the exam?
2.5 hours. But you need to be ready. You cannot try to understand it and then try it first time, right? During the exam, you need to know what you're doing there.
So 2 hours and 30 minutes, it's will include the 15 minutes or without the 15 minutes for scanning?
Are you bargaining? I'll give you additional 15 minutes. This is not the issue. Time is not going to be. Time will never be the issue, because if you know your work, you're going to do it right away. If you don't know what you're doing, you can take forever and never finish it.
Yeah, for sure. But sometimes for me, I'm talking about myself, even if I know and I feel that there's no time to finish it, I keep stressing myself and I keep thinking about the time and forgetting how to do the
Time will never be the issue in this exam. Your problem is going to be knowing the stuff. This is why it is open notes. So there's some challenge here. You really need to know it. You cannot try it on the day of the exam, during the exam, and try to solve
for sure.
Right?
Yeah, for sure.
Okay. All right. And just so you guys know, don't feel shy to ask the question, because I know that some people would feel shy, but others would have the same question. No one would say it. And then you will try to reach me out, right? Let's say in the office hour, you try to understand what's going on. But maybe if you ask now, you can help yourself and help others. All right. Let me ask you here a few questions. You guys know all of these limits, right? You have it in materials. You have seen these limits, correct?
Yes.
Yes.
You have seen this equation. So when F primes go up, what's going to happen to EC? Modulus velocity. Does it go up or goes down? Yes? When F prime C goes up, what happened to EC? The modulus velocity for concrete. Does it go up or goes down?
I think it goes up.
All right.
Goes up.
Okay. Do you gain more strength with time or less strength?
More.
More. Okay, good. After how many days you reach 80% of the strength of the concrete?
10 days.
10 days.
10 days. Considering what? Cement type 1 or type 3?
Type 1.
Type 1. And which type of curing?
Moist cured.
Good. What happens if I have a steam cure and I have cement type 3? Do you know how to do these two values quick? Do you know how to use them and find out the strengths? You remember this equation that we used in the past? Yeah, 75% after 2 days. Okay. So I guess you guys know how to use this equation. Am I correct?
Yes.
Okay,
Yes.
good. All right, excellent. You understand the difference between creep and shrinkage? When you have more creep, would you have more losses or less losses? With creep and shrinkage, generally speaking, when you add them up, when they go up, what's going to happen to the shrinkage losses, to the losses, generally speaking? Would you have more losses or less losses? Let me show the equation so that you can decide. Creeps go up, elastic strain goes up, shrinkage goes up. What's going to happen to the losses? Goes up, correct? Your pre-stress loss is going to increase when you have more creep and more shrinkage in the concrete. Okay. Which one do you think is going to have more losses? 416 stress relief or low relaxation strength? Which one? Again, anyone remembers this?
416 low relax.
Does it lose more or this one loses more? Pre-stress.
Oh, A416, the stress relief loses more.
Loses more, okay. And you know by comparing these two values, right?
Yeah.
At one point, you would consider the concrete is cracked. At one point, would you consider the concrete to be uncracked? What's the definition of uncracked concrete? When what? Yes? What is the cutoff point between cracked and uncracked concrete?
The Never mind.
It's right here. I mean, I give you the answer, I guess.
That's at 7.5 root of
So when the stress in the tension side is going to be less than 7.5 square root of A prime C, you're going to call it uncracked, correct?
Yeah.
Once it goes above 7.5 square root of A prime C, you're going to call it cracked. This is by definition. Uncracked, cracked. See the difference? Transition, and then you call it uncracked or cracked. This going to be uncracked. All right. I guess now you have an idea about the exam. Any questions for me?
Are we having any conceptual questions for the exam or just?
I just went through this already with you guys.
Okay.
Here's one of the questions. If the tensile stress is equal to 6 square root of A prime C in the beam, would you consider it to be cracked or uncracked?
Uncracked.
Okay, I guess you answered one of the conceptual questions. Now, which stress is higher? Is it FPI or FPE?
FPI.
FPE.
FPI is higher?
FPI.
FPI.
FPI, all right. Let me show you some of these conceptual questions. They're all simple. You guys, you should be able to have it right away. I mean, you see this? Would that help you somehow? Which one is higher than what? I mean, which one is higher? Is it the ultimate, FPU or FPI? When you see a question like this, where do you go? You go either to materials or to one of these examples, right? And then you look at the values, and then you answer the question. How much is the assumed losses on average? Can I say it's gonna be 10%?
20%.
Where'd you get? Oh, it's right here.
Yeah.
You're gonna have this type of conceptual questions. You need to read all of this and be sure where to find the answer. I'm not gonna say here you need to memorize the answer, but you need to know where to find it, right? This is gonna be very important thing for you. I'm not asking you, I mean, I cannot memorize all the values, but when I see a problem, I need to know where to go. Even when I do business, right? When I'm at work, I usually have a binder, I have tabs on the binder. Sometimes I have the electronic. I mark it somehow, right? Otherwise, I cannot get to it. It's gonna take me forever to get to it, right? So the way I study my work or my, I'm gonna say manuals and notes, that I need to put notes. I need to put notes for myself. When I have a problem about this, I need to go to the slide number, right? So I can jump quickly to it and answer the problem. It doesn't make any sense that during the exam, I'm gonna be just going through the notes and find out the answer. It's gonna be too much. Yeah, the exam is gonna be covering everything that you have studied in this course. All the slide sets. Not today's lecture. Excluding today's lecture, which is this one here. Any questions before I let you go?
Yeah, Professor, I missed the sign-in at the beginning of class.
The what?
The sign-in, like roll call.
Oh, okay. So that, right?
Yeah.